motivation in creating this system was to design something similar to the local positioning system, but a system that operated locally, so within a range of about 1 meter, and accurately, so with an accuracy of about 1 millimeter or so. Unfortunately, electromagnetic waves used in the local positioning system travel too quickly to accurately sample with inexpensive clocks. So we instead decided to use ultrasound waves, which travel much more slowly, around 900,000 times more slowly, and are much more realistic to capture and sample within our budget range. Our ideal goal for the semester was a high accuracy system with fast update rates, low power consumption, and a relatively low cost. So our focus for this semester was to develop a proof of concept. We set up a circuit that was 2 transducers, a receiver and a transmitter, and we tried to gauge the distance between them and see how accurate we could get at what kind of metrics we could establish. And we were quite successful. We managed to, our results were essentially a maximum error of 2.7% and an average error of less than 1%. That was about a week ago. We've actually significantly improved those figures since then and are getting an average error of around 0.5%, it looks like right now. We had some challenges while designing the circuit, namely device characteristics. We had some problems with op amps. We had some weird wire crosstalk issues while designing the circuit, which were amusing to deal with. And we had some transducer resonance issues that really put a stall in sort of our progress for a while. Next semester, looking forward, we'd like to deal with those transducer resonance issues. A best case scenario would be to get a one-to-one correspondence between the signal we transmit and the signal we receive. But even if we don't achieve that, we'd still like to reduce the amount of time the receiver circuit spends oscillating. That way we could have faster update rates, essentially. Next, we'd like to develop a signal encoding and correlation link that gave us a more accurate timestamp of the receiver, so we'd be able to more accurately calculate a distance. And lastly, we'd like to expand 3 dimensions to make it essentially a position tracking system. Right now, we've got the basic concept established, but we haven't yet sort of layered on the extra dimensions that will make it sort of a viable product. So we'd like to thank you for listening to this presentation. I'd like to open the floor to any questions.
Within a 1 meter position,
yes.
What kind of application would you do?
Oh, yes, my apologies. So industrial processes, things like CNC machines, any sort of robotic vision, a wide variety of commercial applications. We eventually want to set it up so that it can output any of the measurements it makes to a computer, and we can track in real time, like somebody moving the transmitter through any sort of free space within that distance.
You said that you would like to expand to 3D, but are you currently 1-dimensional or 2-dimensional?
It is currently 1-dimensional, but the concepts we have, our transceivers have a 60-degree radius of transmission, so if we layer them appropriately, it shouldn't be too difficult. And Matt has sort of thought of ways we can essentially encode the signal that we like to see come out of it.
Right. Well, the idea is to use either a time division or a code division method for encoding the different signals. The problem that we're running into is ultrasound devices are beats electric. So whenever you apply a pulse, the pulse is a lot longer than the pulse that you initially put in. So before we can begin